Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 9 on solving linear inequalities. Now, in the last lesson, we looked at how we could determine whether a particular value of a variable made an inequality true or false. Today, what we'll be looking for is techniques that will allow us to actually figure out those values. Because of course, just like equations, it's the values of the variables that make an inequality true that we then consider solutions to the inequality. So let's jump right into it and talk a little bit about properties of inequalities, right? So the properties of inequality. We need to use properties of inequality to solve inequalities in much the same way that we used properties of equality to solve equations, right? So we want to understand the rules by which inequalities play by, right? Because they do, just like equalities, inequalities play by certain rules. So let's take a look at exercise number 1. Consider the true inequality 4 is less than 8. All right, so let's talk about this a little bit. What we're going to do is just like with equations, what I'd like to do is take this inequality and play around with the two sides of it. Add the same numbers, subtract the same numbers, etc., and see if the inequality continues to be true. Let's do letter A together. Let's take a look. If we add 3 to both sides of the inequality, what is the resulting inequality? Is it true? All right, well, let's do that. All right, we currently have 4 is less than 8. Let's say I add 3 to both sides of the inequality. The resulting inequality is 7 is less than 11. Yeah, that is still a true inequality. So it appears like if I have an inequality and I add the same thing to both sides, it will continue to be true if it started off as true. What I'd like you to do is finish this problem, do letters B, C, and D, and see if each one of those manipulations continue to produce a true inequality or if one of them maybe produces something that suddenly is false. Pause the video now and work through every one of the remaining ones in exercise 1. All right, let's do it. Letter B. If we subtract 4 from both sides of the inequality, what is the resulting inequality? All right, well, let's see. We have 4 is less than 8. So I'll subtract 4 from both sides and I'll get 0 is less than 4. So that is the inequality I get, and I'm going to say that's still true, right? 0 is less than 4, so it appears that I can subtract the same number from both sides. Letter C says if we multiply both sides of the inequality by 2, what is the resulting inequality? All right, so I'll do times 2 times 2. That'll give me 8 is less than 16. All right, that's true. So it appears that I can multiply both sides of the inequality, a true inequality, and still get something that's true. And finally, if we divide both sides of the inequality by 2, let's see what happens. I'll get 2 is less than 4, and that is also true. So this feels like it's basically what was going on with the properties of equality. Remember, the properties of equality were like the addition property of equality and the multiplication property of equality. The addition property of equality said, hey, look, if we have a true equation, we can add or subtract the same number from both sides and it remains true. And the multiplication property of equality said that we can multiply or divide by the same number on both sides of the equation and it will remain true, so long as we don't try to divide by 0 on both sides. So it looks like inequalities play by exactly the same rules that equations do. Or do they? All right, let's take a look at a very important exception, right? It seems, just to emphasize, from the first exercise that the properties of inequality are the same as the properties of equality, right? Essentially, perform the same operation on both sides of the equation / inequality and it will remain true. But there is one big important exception. All right, and let's take a look at that in exercise number 2. Returning to our true inequality, 4 is less than 8. Letter A, if we multiply both sides of the inequality by -2, what is the resulting inequality? Is it true? All right, well, let's take a look. It certainly remained true when we multiplied both sides by +2. Let's now do -2 times both sides, right? So if I do that, I'll get negative 8 on the left-hand side is less than negative 16 on the right-hand side. Now you have to be careful, right? Negative 8 is less than negative 16. Well, that's actually false, right? Because negative 16 lies to the left of negative 8 on a number line. Negative 16 is actually less than negative 8. And if you want to think about it in terms of temperatures, or I don't know, how far underwater you are, or what have you, right? This is actually a false inequality. Let's actually look at letter B as well. If we divide both sides of the inequality by negative 2, what is the resulting inequality? Is it true? So again, we have this true inequality, 4 is less than 8, right? What happens if I divide both sides by negative 2? Is this still true? 4 divided by negative 2 is negative 2. 8 divided by negative 2 is negative 4. Negative 2 is less than negative 4. That's actually false, right? So, what is our upshot here, right? Let's take a look. The properties of inequality. The addition-subtraction property of inequality works exactly the same way as it did with equality. If A is greater than B is true, then I can add the same thing to both sides of the inequality and it still is true. Okay, so nothing changes when it comes to adding and subtracting from both sides of an inequality. Okay, nothing changes at all. And by the way, that kind of makes sense because if you think about two numbers on a number line, right, if you think about this, right, and you think about the one on the right being bigger than the one on the left, okay, if I add, if I add to both of these numbers, it just takes them both and it shifts them to the right. This one is still larger than this one. On the other hand, if I have the two numbers and I subtract from both of them, it just shifts this way and this one is still larger than this one. Okay, so it doesn't really matter. The relative positions stay in the same places. The one on the right still is larger than the one on the left. Now, the multiplication division property. If A is greater than B is true, then C times A is greater than C times B will be true if C is a positive number. And that also works for division, right? So in other words, if I multiply both sides of an inequality by a positive number, or divide both sides of an inequality by a positive number, then the inequality remains true. And again, you can still think about it in that positional way, right? If I have two numbers like this and I multiply them both by 2, right, they'll both kind of get farther away from the origin, but the one that was on the right will remain on the right. On the other hand, if A is greater than B is true, then C times A is less than C times B is true if C is negative. And the reason for that is very simple. When we multiply or divide by a negative number, the two numbers flip so that their relative positions are opposite of each other, right? So now the one that was on the left is on the right, the one that was on the right was on the left, right? Most of the time, the vast majority of the time you have to worry about this is when you divide both sides of an inequality by a negative. And as soon as you divide both sides of an inequality by a negative, to keep it still being true, you have to switch the direction of the inequality symbol. That is certainly something that you saw in middle school, okay? But it's also one of the most mysterious things about inequalities. And again, it's all about the fact that when you multiply or divide by a negative, right, then the numbers change sign and they kind of flip-flop on the other side of 0, okay? So let's take a look at that one more time. Let's take a look at exercise number 3. Write a true inequality and show that it becomes false when multiplying or dividing, your choice, each side by a negative. So that's what I want you to do. I want you to pick an inequality, any inequality with two normal numbers that's true, and write it down, whatever you want. And then I want you to either multiply or divide both sides of that inequality by a negative number and show that that inequality has now become false if you don't change the direction of the symbol. All right? Pause the video now and come up with your own example. This is a great problem to kind of compare with your friends because, again, if you're truly doing it independently, you could be all over the place, right? For instance, you could go to something simple, like let's say 15 is greater than 10, right? Definitely like a true inequality. 15 is greater than 10. Now let's say I multiplied both sides by -2, right? So I do -2 here times -2 here. So this original inequality was true. Then I multiply them both. I get -30 is greater than -20, and that is certainly now false. You could even go with one number that's positive and one number that's negative. For instance, you could say something like -8 is less than 2, right? Which is certainly a true inequality. Let me do a little division here. Let's say I divided this by -1 on both sides, right? If I did that, I would then get 8 is less than -2, and that's false, right? The original one is true. That one then is false, okay? Now, in all practicality, right? In all practicality, what's really going on here is an instruction to us to say, if we're solving an inequality, just like we solve an equation, we want to isolate the variable. If we do that and we divide or multiply both sides of the inequality by a negative number, we must switch the direction of the inequality, or whatever answer we get is going to literally be the opposite of what we want. Let's see how that pans out when we solve an inequality. All right, solving a linear inequality. If there is no multiplication or division of both sides of an inequality by a negative, we can solve it in the identical way as we would solve a linear equation. All right, so let's take a look at that. Exercise number 4. Given the linear inequality 4x minus 3 is greater than or equal to 5, do the following. A, solve the inequality by applying the properties of inequalities that we found earlier. All right, so let's do it, right? Properties of inequality we found earlier were, you can add two things to the same side, not switch the inequality symbol. You can divide by, as long as what you're dividing by is positive, all that. So what do? Well, we're going to just write down 4x minus 3 is greater than or equal to 5. I can add a 3 to both sides. That doesn't change the truth of the inequality. 4x is greater than or equal to 8. I can divide both sides by 4. That's not going to change the truth value of the inequality. And I get x is greater than or equal to 2. Right? X is greater than or equal to 2. Now let's take a look at letter B. Right? It says, write 5 numbers that make the final solution true and plot them on the number line below. In other words, like, I want 5 numbers that if I put them in for x would make that a true statement. Well, one number that would certainly make it true would be 2, right? 2 would make it true because 2 is equal to 2. So let's, 5 numbers. Well, 2 would make it true. Anything bigger than 2 would make it true, like 2.1 or 3 or, I don't know, 7 or 9. That's 5 numbers. And if I plotted them on the number line, right, I would, like 2 would work. I don't know why I did 2.1. Let me do 2.5. That's a little bit better. That's right here. 3, that's here. 7, that's here. 9, that's here. Right? And the idea is, when I'm writing down these numbers, is that it gives me a sense for how I can graph the solution set. You see, in a normal equation, we might solve it and get 1 answer, 2 answers, 3 answers, right? Here, every value of x that's greater than or equal to 2 is a solution. And that means every value of x that's to the left of 2 and is equal to 2 is a solution. So I show my solution set by putting a nice solid dot on x equals 2 and then drawing a thickened line with an arrow to the right. Some students don't like to do that on the number line, so they'll do it above the number line. I think that is completely acceptable. All right, so whichever one you find more comfortable. Now, if this was a multiple choice question or something like that, they would have the shading on the number line itself. But a lot of students find it kind of easier to really show their work up here. And again, it's saying if I took any number that's shaded here and I substituted it back into this original inequality like we did in the last lesson, that inequality would be true. Now let's take a look at one that's got that special exception to it. All right, watch for division by a negative. Inequalities can get tricky if you divide both sides of them by a negative number in order to isolate the variable. All you have to remember is when you do that, you must switch the direction of the inequality when that happens. All right, now let's take a look at a classic example, exercise number 5. Given the linear inequality 8 minus 2x is greater than 16, do the following. A, rewrite the left-hand expression as an equivalent expression using addition. Let's do this together. Here's what I mean, right? On the left-hand side, I have the expression 8 minus 2x. It may be easier to think about that, instead of having 8 minus 2x, as negative 2x plus 8. Do you absolutely have to do that? No, not particularly. But I kind of love having that variable first, right? And remember, that negative 2 is attached to it because it's really 8 plus negative 2x. Now, let's take a look at letter B. Solve the inequality by applying the properties of inequalities. Okay, great. This is literally almost exactly what we did before, right? I'm going to have negative 2x plus 8 is greater than 16. I'm going to subtract 8 from both sides. Now, when I do that, I don't switch the inequality because I can subtract or add anything I want. But now, I have to divide both sides by negative 2. And as soon as I do that, that flip-flops into a less than symbol, and 8 divided by negative 2 is negative 4, right? So I've got negative 2x is greater than 8. That's very true. But as soon as I divide both sides by negative 2, I now have x is less than negative 4. Okay. Letter C. Pick a number that is true based on your solution to B and show that it makes the original inequality true. All right. In other words, right, this seems to be saying that if I take any number that's less than negative 4, now think about that. Numbers that are less than negative 4 are numbers to the left of negative 4 on the number line, right? Negative 4 is right there. So any numbers that are out in here are left of negative 4 and should be less than it. So if I pick any numbers out in here and I substitute them into the original inequality, they should make it true. Pause the video now and you pick a number out there, substitute it into the inequality, and show that it's true. All right, well, certainly a good choice would be, let's say, x equals negative 5, right? X equals negative 5 is certainly less than negative 4. So then if I substitute it into the original inequality, right, which is 8 minus 2x is greater than 16, give myself a little more room, I'll have 8 minus 2 times negative 5 is greater than 16. I'd have 8 plus 10 is greater than 16, and 18 is greater than 16, and that is true. One of the reasons I like doing this is that if I had, in letter B, if I had made the mistake of not flipping the inequality, right? Let's say I made that mistake. I would have gotten a final answer of x, actually, let me put this in red real quick. Right? I would have gotten a final answer of x is greater than negative 4. So that's wrong. I want to be very clear about that. And then if I had said, well, let me pick a value of x that's, that makes that true. X is greater than negative 4. I could have been like, well, negative 3, right? And if I put negative 3 in here, I'd have 8 minus 2 times negative 3 is greater than 16. Negative 2 times negative 3 is 6, and I would have had 8 plus 6 is greater than 16, and I would have had 14 is greater than 16. Well, that would have been false, right? And I would have said, well, wait a second. Something funny happened there. And it would have been false because I didn't flip the inequality symbol when I divided by a negative. We go back to blue, since red is a little harsh. Okay, so now let's talk about how to graph this. Now, this is where things can get a little tricky for students. The correct answer is x is less than -4. So let me just wipe this out so we don't get confused by it. X is less than -4. Now, that is all the numbers to the left of -4, but it doesn't include -4, right? Now you might think, well, then I should just do -5 and left. But that would actually leave out the numbers that are between -4 and -5, like -4.5, -4.9, -4.999, etc., right? So what do I do? In the case where there's no equal sign, notice no equal sign, I'm going to draw an open circle around my -4. Okay? That indicates that it's not part of the solution set. And then I'm going to extend that line that indicates that my values are less than -4. Again, if you want to do it above the number line, that's cool as well, as long as it's pretty obvious what number you're circling, right? Oh, I'm circling -4 and I'm going to the left. If it included -4, I'd want a filled in dot on the -4, like I had in the last problem. Okay, let's take a look at one more. Now, one thing that we haven't done so far is we haven't had to do any kind of manipulations on the left and the right-hand side, but you may have to simplify each side of the inequality before isolating the variable. When you do this, you are using properties of real numbers like the distributive, the commutative, the associative properties. These will not change the direction of the inequality because you're operating exclusively on the left-hand side or the right-hand side to produce equivalent algebraic expressions. You are in no way using properties of equality or inequality. So let's look at this beast of an inequality in exercise number 6. 8 times the quantity x minus 2 minus 3 times the quantity 2x plus 1 is less than or equal to 7x minus 3 times the quantity x plus 1. Letter A, use the properties of numbers to simplify the left-hand and right-hand expressions of this inequality. Okay, and I really want to emphasize this because I'll get students very confused and they'll say, well, you know, since I multiplied this 2x plus 1 by -3, do I switch the inequality? And the answer is no, right? What I'm going to do in letter A has nothing to do with inequalities whatsoever. Inequalities or equations. I am literally going back to Unit 1, you know, I think like lesson number 2, where I'm just writing equivalent expressions. I want an expression that's equivalent to this, and I want an expression that's equivalent to that. But I'm not going to be multiplying or adding to both sides of the equation or anything like that. So let's do it. Let's go for this together. Right, so on the left-hand side, I'm going to start by writing an equivalent expression by multiplying through by that 8. That'll give me 8x minus 16. Be careful. Here I'm going to multiply through by a -3. -3 times 2x is -6x, and -3 times -1 is -3. Okay, again, I can't emphasize enough. When I did that, all I was doing was rewriting the expression on the left-hand side as an equivalent one. And I'll do some simplifying on that in a bit. But let's now get to the right-hand expression. Less than or equal to, that 7x just is hanging out there. And now I have to distribute multiplication by -3. -3 times x is -3x. -3 times 1 is -3. Now I can do some commutative associative kind of work on the left-hand side. 8x minus 6x is 2x. -16 plus -3 is -19. Is less than or equal to, again, a little bit of combining like terms here, 4x minus 3. Okay, again, I have done nothing up to this point to solve this inequality. All I've done is equivalent expression work on the left and the right-hand side. You shouldn't confuse doing things to solve an equation or an inequality, right, which is things like the multiplication property of equality or the addition property of inequalities or whatever, with just writing equivalent expressions. But now let's take a look at letter B. Solve the inequality using the properties of inequality and graph the final solution set. In other words, right, now what I want you to do is solve this inequality using those properties. Pause the video now and go ahead and see if you can both solve the inequality and graph its solution set. All right, well, let's do it. Let me rewrite it right up here. 2x minus 19 is less than or equal to 4x minus 3. I think I'm going to add a 19 to both sides. Okay, nothing wrong there. It's going to give me 2x is less than or equal to 4x plus 16. I'm going to subtract a 4x from both sides. Again, I don't do anything about switching the inequality symbol. I'll get negative 2x is less than or equal to 16. And as soon as I do this, I need to switch. Now I'll have x is greater than or equal to negative 8. All right. And again, I want you to interpret that statement. X is greater than or equal to negative 8. That tells me that every value of x that's to the right of negative 8, along with the value of negative 8, should be shaded. So I just need to come in here, extend my page a little bit. Here's negative 8. I'm going to color that in because the solution set includes it. And now I just have to put an arrow and a solid line. How long of a solid line, how big of an arrow, doesn't really matter too much. You just are indicating that everything to the right of negative 8, including negative 8, is part of the solution set. Again, really, really critical to understand that as soon as I do that division by negative 2, I've got to flip-flop the inequality sign. Okay, let's summarize. You'll do a lot of work with inequalities over your time in math, okay? More time will be spent solving equations, but certainly you'll have to solve inequalities here and there. They're amazingly important in the worlds of economics, engineering, science, all over the place. And honestly, especially with linear inequalities where you've just got an x to the first, and those will be the only kind we deal with in this course, with linear inequalities, you can solve them exactly the way you solve linear equations, with the exception that when you divide or multiply both sides of the inequality by a negative, you've got to switch the inequality sign. And hopefully, we gave you a lot of examples today that make you feel comfortable not only how to do that switch, but why you do that switch. I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.